All right. So, continuing on through 5, working on, or I should say chapter 5, talking about, the different parts of triangles and how we can use them. So, starting here with the kickoff, use the information given in the diagram. Line CD is the perpendicular bisector of AB, segment AB. Find CA and DB and explain your reasoning. Well, we know from the last lesson, from the last lesson that the perpendicular bisector, if we're on it, theorem 5.2 says that if we're on it, we're going to be equal distant to the endpoints. So if C is on it here, it's going to be equal distant from B as it is to A. So CA has to be 5. DB then, well, D is on it, so the distance from DA to DB would also be the same, so that would be 6. All right. Now, shifting gears a little bit, but we're going to talk about concurrent lines. Concurrent lines are where at least 3 lines intersect at a single point. So if I have a line here, line here, line here, they're all intersecting at that single point. So those would be concurrent lines. Now, that point where they intersect is called the point of concurrency. All right. Now, knowing that, we can do a few things. So we have what's called the circumcenter, which is that point of concurrency where all of the perpendicular bisectors intersect. So the perpendicular bisectors of every side where it comes together here is that circumcenter, where we can draw a circle that would be equal distance from that circumcenter that hits all 3 vertices. So we would say it would be circumscribed about that triangle. That triangle would be circumscribed about the circle. Sorry, other way around. Okay. The other side of this is we have the incenter, which is the inside of the triangle here where the angle bisectors all come together. So right here where the angle bisectors all come together in center, and it would be equal distant to the sides of the triangle, so we can draw a circle that would be inscribed about the triangle. Now, what we can do about it is this. Now, here's our typo for this lesson. Find the center of the circle that you can circumscribe about the triangle with vertices 0, 0, negative 8, 0, so 1, 2, 3, 4, 5, 6, 7, 8, and 0, 6, so 1, 2, 3, 4, 5, 6. Now, if I draw the line through here, this would be our triangle. So it would be a right triangle using the axes. So to be circumscribed, we're looking for that circumcenter, which is this point where all the perpendicular bisectors come together. So perpendicular bisector here would be the midpoint. So 1, 2, 3, 4. And it would be a dashed line cutting through there. This side midpoint, 1, 2, 3. Again, dashed line cutting through there. So right here on that side is going to be our circumcenter. Now, it would have it probably cutting through something like that. Okay. So where that's at is this. So we'd go 1, 2, 3, 4 back. So negative 4, comma, 1, 2, 3 up. So negative 4, 3. Now, at this point is where we could draw the circle that hits all of these sides, and it would be equal distant. Now, my circles looks a little bit more like an oval, but you get the point. So circumcenter, all the angle or the perpendicular bisectors where they come together would be where that happens at. Okay. So that's how you find that. Next, we have the medians. The medians of a triangle are where we go from the vertex, so the corner of the triangle, to the midpoint of the opposite side. Now, with that, we have our theorem 5.8, which is where the medians of a triangle are concurrent at a point that's going to be 2/3 of the distance from each vertex to the midpoint of the opposite side. So from E to C, this midpoint, or where they all come together, is 2/3 of the distance. That means this would be 1/3 of that distance of that median. Okay. Now, where they all come together is called the centroid, which, let's be honest, sounds kind of cool. Kind of like an evil robot cool. Or a good robot, either way. It's a centroid. It kind of sounds like a robot. But that's where they all come together. So how we could do that is this. So D here is going to be the centroid. So that's where they're all coming together. We know DE is 6. So this down here is 6. We're looking for what BE is. Well, we know this is 1/3, which makes this be 2/3 of the distance. So 1/3 of it's 6. So if we take it times 3, we're going to get our full distance. So BE is 18. Now, just for fun, if we know this is 2/3, if we double this, we'd get 12, and that would be our distance. So 12 and 6, boom, 18. Next thing here was we have altitudes. Altitudes of a triangle goes from the vertex to a line containing the opposite side perpendicularly. So from the vertex to the opposite side, we're going to intersect that at a perpendicular angle, so 90-degree angle. So acute, that's going to be on the inside. With a right triangle, it's going to be on the, well, one of the sides. So here it could be this side. If we were doing the altitude from this side, we'd be that side. But it's going to be a side if it's an altitude on a right triangle. Now, an obtuse triangle, it's going to be on the outside. Okay. So, looking at this, will ST be a median, an altitude, or neither? Well, we're going from the vertex to a spot on the other side at a perpendicular segment here. So that would make it an altitude. Now, just for fun, what would be a median? Well, median goes from the vertex to the midpoint. W here is the midpoint because we have a line on either side, meaning these two are congruent. We're being bisected there, so U to W would be a median. And lastly, Theorem 5.9, lines that contain the altitudes of a triangle are going to be concurrent. So you might be going, well, how do we know it's concurrent? Well, let's do one. So altitude for an acute, well, okay, they can all be in the middle here, so that makes sense. Well, if they're both the sides, well, then they have to meet right there. Well, what about an obtuse? Well, if we draw an obtuse here, we know that the altitude would come down, and it would intersect here if we extended this out 90 degrees. Now I'm going to continue with this down. Hopefully I don't run out of room. This other side here, we would intersect at a 90. So if we continue this over, we'd hit there. And then if we extended this out, we would go at a 90-degree angle there. That was not a very good 90, but anyways, there's still a point out here. It might be outside the circle where that point of concurrency all is. So that is it for this lesson. Please let me know if you have any questions. You can pan me, email me, send me a message on Google Classroom. If something didn't make sense, remember, you can always pause it, rewind it, watch it again, try to catch it again. Or if you're writing stuff down and I get going too fast, you can pause it there too, write your stuff down, and then resume it and watch the lesson and hear my explanation. So until next time, we'll talk to you later.